picture of a cobordism. There is a condition to make. So I don't discuss this topology, so he was interested in pictures like that. And there was a Morse function. Another thing that you can do with Morse functions is to consider the gradient flow. And the gradient flow for a Morse function is just a little bit stupid. It just goes up. It does some silly things about this. So this is the dynamical system, but it kind of moves up. And when it meets the singularity, it does something a little bit complicated, but otherwise things are trying to go from here to there. If there are no singularities, you kind of find an equivalence between bottom and up. That's how you prove that two things are homeomorphic at some point. He has to eliminate the singularities. Anyway, there is this kind of gradient flow that he has interest, very trivial dynamical systems. In the last case that his interest, there are no singularities, it's just a complete thing that moves from bottom to top. Trivial kind of dynamics, but he got interested in dynamics. And being a very overly confident guy, for good reasons, but still overly confident, he thought that he had discovered everything already in the first attempt, and thought that everything was more or less Morse-Mail, or more or less this kind of Morse, yes, it became known as Morse-Mail flows. So this Morse functions, mail, blah, blah, blah. So he thought that everything was simple like this, because he didn't know the history of dynamical systems. He didn't know even this picture. Someone comes and tells him, look, chaos exists. We found out before, there are these and that examples, there are more examples than that. It's not like always like this. So then what he does, he's kind of annoyed, but then he does better. He understands qualitatively this picture. He goes to Rio de Janeiro, goes to the beach, and as he says, he found the horseshoe there. He found a horseshoe at the beach, like in his mind, which is a picture that describes this. So that he says that everything that's going complicated in this picture comes from a simple drawing that you can do here, which you take a square. So now my dynamical system is discrete. It shrinks in this direction. It stretches in this direction. This would not do much, but then it folds. So it's called a horseshoe for obvious reasons. And you do this map. So the rectangle, tack, tack, and fold. And he says, if you look at the dynamics of this rectangle, you are going to say, to get the complicated things here. So here you have these features that was present on this picture here, that was stretching and so on, and there was this kind of a little bit of folding. And here you get this. So if you take a trajectory here, and nearby trajectory, there will be trajectories that will be going up and down, and they have to do things like this. After you iterate a little piece of trajectory, it kind of contracts, and then stretches, and the stretching kind of combines. I cannot, not very good at drawing, and so on. So he said, and he went further, and using this model, he said, well, that's what happens whenever you have this kind of unstable equilibrium, and then you have this kind of whatever homoclinic point here. So you have this unstable, and you go through an homoclinic point that appears here. So this generates this crossing. As you iterate, it will fold itself into a horseshoe. So it's just a geometric model for what was there. But with the geometric model, he can give a coding, and he can prove theorems about the persistence of the chaos in this. So he showed that there was some kind of persistent chaos associated to that nevertheless could be understood. So next, he gets overly confident again. This works, and says everything should be like this. Almost everywhere, this should describe almost everything. Again, it's wrong. He found himself some counterexamples. So actually, most chaos is not stable. So that's what happens. So you cannot describe things in terms of stable chaos. Chaos is there, but it's more complicated than just this chaos that's stable. Like this one was good. He found the model of stable chaos. So you have this picture that he understood. So next, we get to how badly things are with Newhouse, which is the person who understood how those two pictures, this picture can kind of enhance once more this one to get a kind of especially unstable chaos. So now this object here is associated to having a single unstable point, and it's generating all this. Now, you can consider this kind of thing, which is a kind of unstable set, which is a fractal set. This will generate a counter set of instability. So actually here, you can imagine that you can enlarge by picking this picture and adding this picture here. So you add enough complications here coming from this here. You add actually a counter set of instabilities here, right? I don't make the pictures here, but imagine that through this counter set, so a lot of points, you can copy this picture here. So you're going to get now, geometrically, through a counter set here, you get all those unstable orbits leaving. So you get a counter lamination emerging from here. And there is through this counter set, there is also things that come to the counter set, right? There is a stable lamination. And they fold and interact. So there will be a picture here that they come here, and then they make some complicated picture. So now the interaction between those two laminations becomes a source of chaos, a more complicated source of chaos. How bad it is? Well, so Smail showed that if you had a homoclinic point, but the homoclinic point was transverse, it generated some good chaos. Transversality is normally good. He came from differential geometry, so he was used to Whitney and so on. Transverse intersections persist, and that's generated some stability. That's how his argument goes. But in this picture, there are tangencies. So what Newhouse was interested was in understanding how this kind of tangencies could appear in a persistent way between some kind of fractal objects. You understand how tangents appear in this between just two curves, and they unfold to transverse intersection. But what happens here? Can you have some persistent tangencies? So he found out that you can, and it's coded by this geometry here. It's a geometry of the counter set. Here, again, connecting to topology, if you want to try to understand the general picture of manifolds intersecting, what do? You put, so you're allowed to perturb and so on, and try to understand the perturbations. You count dimensions. You look at the dimension of the ambient space, and then you have two manifolds. If the sum of the dimensions is bigger or equal of the ambient space, you may have small, you can just put them apart. And basically, it becomes the problem of understanding how some fractal objects intersect, but trying to understand how they intersect even after perturbation. It's some kind of transversality for fractal sets. You want to do this. You now have two counter sets. For some reason, you can project along the laminations, and everything happens in the line. So you have two counter, and you have another counter set. And you ask if the counter sets intersect. Those are fractal sets. They live in the line. But more than that, you want to know if after you change a little bit the dynamics, what will happen? Are they still intersecting or not? So it's a new theory that's necessary. So it was shown at least some exists. It's still not completely understood, but now so Newhouse gave a criteria for the geometry of the two counter sets. So he proved that this happened. And he went more. In the end of the 70s, he showed that any time that you get a picture like this, right, so any time that this picture appears at all, and it just appears for the first time an homoclinic bifurcation, so appears this thing that was nice. So the picture since from Newton, it immediately generates this kind of stable intersecting counter sets. So these complications that appear here are inevitable once you change from this here. So what theorem this implies? Then he shows that, for instance, forget about conservation laws for the moment, but suppose that you had, for instance, a dissipative system. So area is contracted, right, not preserved. So it can prove that there exists. So there is a theorem that is called Newhouse. In the Newhouse domain, it's the region in parameter space where those contour sets stably intersect, in the Newhouse domain, there is the dynamics is extremely complicated. And in fact, he showed that generically, you have infinitely many attractors. Attractors are annoying because you expect an attractor that it carries out an open set with this. So you expect that you could, for dissipative dynamics, that you could break your system into finitely many pieces governed by an attractor, but not in the Newhouse domain. They have very tiny basings. They are appearing, disappearing all the time in this infinitely many, but in this whole open set, you kind of keep it. And they are generated by this stably intersecting contour set. So he gets this thing saying that, well, as long as things get complicated, they get very complicated. And now many people spend a big part of their lives trying to understand this Newhouse domain. There are many more things. This is just the beginning. That's one of the first Newhouse theorems. But then there are many more complications. So, okay, this looks a little bit complicated, but let's make it a little bit more. All this, I was making pictures in 2 dimensions, except this that was just a manifold. So there was pictures in 2 dimensions, 2 real dimensions. Because I was interested in real systems that arise from this. But mathematicians like to do some other, to generalize and so on. So you can consider what happens for complex dynamical systems, right? So it should be making my life even more difficult to draw. And so what happens when you consider complex dynamical systems? You get some more complicated fractals. Instead of having contour sets, you get some sets in the plane. It should correspond. So I look at dynamical systems in 2 complex dimensions. So imagine that everything that I drew, actually, every curve looks like actually a piece of a Riemann surface that appears here, and everything is living now in situ. And now what corresponded to a contour set on the line becomes some kind of complicated set on the plane. And you would have a picture here of sets like this intersecting. So the theorem, so there is a theorem behind the talk that I'm trying to simplify from more. So let me just say that the theorem that we prove with Liubich and Zhuang Zhang is that the Newhouse phenomenon, everything that I talked here, holds also in complex. So I'm being a little bit sketchy here because what we prove exactly that is that whenever you have a homoclinic bifurcation in the complex domain, you're still getting the same complications here. All this is excuse to show a picture. Let's see what happens in the complex. There is a computer. Okay, so I need a password, I guess. So in the complex, there is a symbolic fractal that dominates. The fractals are not like this contour dust. You have a better fractal, which is there. So that is the famous Mandelbrot set. So that when you look in the plane, in the complex plane, things look much prettier. They look like this. So this is the kind of object that now you're interested in. It's not just some kind of contour set, which doesn't have a lot of personality. A contour set, you just describe a few features. What's the size of the holes and things like this. And then there are concepts that capture a lot, like house of dimension and so on. But here's what you have to worry about. So this is a classical contour set, a classical fractal set. Let us look how nice it is when you amplify. This is a particular piece of the contour set, of the Mandelbrot set, when you go through the cusp. And let's look at this kind of, what we get. It takes some time to do. It's forming here what look like a sequence of elephants, one after the other. This part of the Mandelbrot set is called the Elephant Valley because of those elephants. And they are just following each other. And a mathematician called Mitsuhiro Shishikura, He investigated this area, and to study the fractal properties of the boundary of the Mandelbrot set, and he proved that the boundary of Mandelbrot set is very complicated. It has dimension 2, the boundary of the Mandelbrot set. And it's because of analyzing those elephants. There are many reasons for that, but that's where he did his work. So look at those elephants, and notice that they have a very nice structured behavior. So because of this structural behavior, this analysis of Shishikura, you find that some contour sets that appear when you do this whole analysis, they are very orderly. The elephants look nice, but in fact, there is some order component appearing here. That's just one thing following the other. But there are 2 dimensions, so it kind of, you get some kind of lattice structure of those contour sets. It's difficult to see in the elephant, but it's behind the elephants, you can imagine. So you have contour sets that look kind of very orderly. And the basic idea of the proof of this theorem is a new technique to try to show that 2 sets, they are going to intersect stably. So it's transversality property for fractal sets. But now, what's exploited here is not simply the concept of dimension, which is kind of underlying what's doing this. So concept of dimension, I said dimension of manifolds, that it's house of dimension of fractal sets. You need to have big enough dimension. So you have a concept here of matching contour sets. So you have one contour set that is generated by something very orderly, like so there is order on one side, and a kind of random contour set here. So there are 2 that appears. On one you see order, and in the other you see just disorder, normal disorder that appears. That's what you expect from anything, that there will be some disorder. So this is coded into a recent gadget. That's something that's being developed and becoming fashionable, is to study fractal sets by looking at the notion of Fourier dimension of the fractal set. So Fourier dimension means you have a fractal set, you put a measure on the fractal set, and you take the Fourier transform. And if the Fourier transform decays, it means that there is not too much order. It's a way to say that the fractal set is a little bit fuzzy. And somehow, if you match the most orderly of the contour sets, the ones that are kind of have a lattice structure, that are appearing for some mysterious reason with those elephants, and they do appear after you do the bifurcation, if you mix this with just like anything that will present some chaotic properties, the conflict between the order of the lattice and this a kind of a disorder measured in this Fourier decay, they will produce exactly what you need to link those 2 objects for that. The explanation of this use a technique that's called one of the many instances that has renormalization. Here there is renormalization, and this is yet an instance of renormalization. Don't explain what renormalization is, but some tool that allows you to put a microscope here and resolve sets until you detect that they kind of are actually intersecting. Okay, so I tried to make a 1 hour and a half talk in 30 minutes by simplifying a lot. Maybe with questions, it will be
Thank you.
Fine.
We maybe only have time for 1 question. Is there a question from the audience? If not, maybe we should just move on. Yeah, okay. All right. So let's thank Professor Avila. So thank you, Professor Avila, for a very attracting talk. All right. So our next speaker is Professor Shouwu Zhang from Princeton University. The title of his talk is Elliptic Curves and the BSD Conjecture. Let us give him a warm round of applause.
能听见我说话？Sorry, I speak Chinese. So, and thanks for inviting me to give this lecture. And I answer very fast, but until a few days ago, then I suddenly realized that I have no idea what kind of talk I'm supposed to give, because they say I have a physicist, even high school students, and of course a number theorist here. So I decided to talk about, during the banquet, Bong Liang told me maybe you should talk about elliptic curves. So I can talk about elliptic curves. This is a very special year for elliptic curves, because the most major theorem was proved in 102 years ago. And since the proof of the model VA theorem, then the developments, the role played by elliptic curve in number theory is become more and more important. So you know that until we, on a Sunday, the announcement of Andrew Wiles won this prize, largely due to his breakthrough and the arithmetic through elliptic curves. But the elliptic curve itself is not invented, is not in this century. It basically starts with Euler's work to study the arc length of ellipse. So the reason called elliptic curve, because it's related to the ellipse, right? For circle, we know how the usually we call the angle. The standard definition of angle is the arc length of the circle. But you may immediately ask the question, what is the arc length of ellipse, right? Then you start to do it, you find that it's a very simple integral. Usually it's the dx over square root of some cubic polynomial, right? That integral immediately we don't know how to do it. Okay, since we don't know how to do it, it's a new mathematical object. So that starts with Euler, but it's completed by Jacobi and Abel. It took 100 years to finish it. So during the new century, 20th century, Poincare took the business. Then he started to put the elliptic curves in the elliptic equations. He redescribed this addition law written in the very algebraic formula. But we have to remember the beautiful theory really goes back to Euler, Abel, and Jacobi. In mathematics, mathematics is the language of the natural science, so we know that. And so mathematics usually, we start with the basic axioms, right? Then trying to build up every block, use these axioms. And by other hand, mathematicians also propose some questions. So in fact, so the use of elliptic curve, in fact, goes much more than 200 years. It's got 1,000 years. So my lecture will start with, I will not give a formal definition of elliptic curves. I think you can find it in the internet. Also, I will not give a formal definition of a BSC conjecture. But I will tell you why elliptic curves is useful and why BSC conjecture is useful. So I will start with an older problem. So this is called Arab puzzle, discovered at least in the 1972 in a manuscript in Paris. So this manuscript asks the following question. So today we call it congruent number problem. So given an integer, find rational squares, gamma square, such that gamma square plus and minus n are both squares. So in other words, given the integer, to check which integer is in fact the common difference of the arithmetic progression of 3 rational squares. So this integer is called a congruent number. So this can be found from Dixon's history of numbers in 1920. So they immediately, by using the, immediately found some different formulation that's much more popular in these days. And so this finder, so it's about which integer is the area of the right angled triangle whose three sides are rational numbers. So that's the basic problem. So, for example, we have three right triangles. The sixth is the one we use very often, 3, 4, 5. Then, in fact, 5 or 7 also the congruent number. This is somehow in the history books due to the Fibonacci. So Fibonacci basically figured out, I mean, probably the challenge of scholar, he wrote the answer for 5 and 7. 6 was known. It took 400 years later to prove that 1, 2, 3 are not a congruent number. So, so I write this story there. So in one Christmas evening, Fermat wrote a letter to his friend. He said, I discovered at least a most singular method, which are called infinite descent. At first, I use it only to prove negative assertions, such as there's no right-angled triangles in numbers whose area is a square, right? But if you right-angle the square, you can divide the number, become 1. If the area of such a triangle was square, then there will be a smaller one with the same property, and so on, which is impossible. So this is called infinite descent. And this principle of infinite descent becomes a major number theory too, even as today. Then I found some solution besides these 1, 2, 3, or 5, 6, 7. Then for some of the solution, it can be very big. So the number of solutions doesn't depend how thin the small. The 157 is a pretty small number. It is a congruent number, but to find the solution is not a completely trivial business. Of course, this is Zaghi as a solution, but Zaghi doesn't do it by hand. They have a theory behind this thing. This is the major purpose of my lecture. So what kind of theory can be used to find such a solution? So then, for these days, people believe there's a way to make a general principle. So that's a kind of mathematics. We cannot, like physics, ask a very general question. Number theories usually start with very special example of a lot of experimental work, then make up a general principle. So the general principle is like that. If it starts with a square-free positive integer, positive integer means the natural numbers. So if n is congruent to 5, 6, 7 mod 8, then n is congruent. This is a very definite result. Doesn't matter how complex the number is. This is a congruent number. But as I said, that how to find a congruent number could be a very difficult issue. On the other hand, if n is congruent to 1, 2, 3 mod 8, then n has a probability 0 to be congruent, right? So I will define what does it mean. Does it mean the following? If it starts with a bigger number, so x is n less equal than x, n congruent to 1, 2, 3 mod 8, and is congruent. This small set is very small. It's compared with the general sets, in fact, it's 0. This is a general conjecture. This conjecture only made is very recently, no more than 50 years. So the result is accumulation of many, many people's work. So most recent people who done definitely the contribution is Ye Tian, and he was he's probably here somewhere in the audience, and one undergraduate from Princeton that time, Alexander Smith, but now I think he's a Clay Fellow at the UCLA. Oh, then I guess a missing. Sorry, there's a missing. There's a slide missing some parts. Okay, so the part is the following. So this conjecture is known for an explicit set of numbers containing more than 50% of the number congruent to 1, 2, 3 mod 8, and another 50% congruent to 1, 2, 3 mod 8. And so that's the best result we can do. Even this result depends on very recent advance of the number theory. So before going, I have given you an elliptic version. The elliptic curve version is like the following. For a positive integer n, find a rational number point xy with a non-zero y on this elliptic curve. So I will not define the elliptic curve. The elliptic curve is a curve can be written down as the equation. One side is just a square, other side is a cubic polynomial. The proof is just Euclidean formula for Pythagorean triples. Because as I said at the beginning, the congruent number is related to the right triangles. So more than 2,000 years ago, Euclid already have a formula for these triangles. So you bring this in, you will get this thing. So this is not a difficult thing. This is why people believe the elliptic curve already been studied more than 1,000 years ago. So I give you some idea about the real and the complex points. So this is the real points. Real points is a curve, is a circle, other side, more like a circle, other side like this. So this circle actually has a group law. The group law is given by P and Q. You take a line, you intersect with the third points, R, then you do a reflection. The reflection gives you P plus Q. So group law is simply by P plus Q plus R equals 0 if and only if these 3 points are in a line. But to prove this, in fact, the group law is highly non-trivial because, for commutativity, it's easy. For associativity, it couldn't be math if you're trying to do by hand. As I said, this was discovered by Euler, Albert, and Jacobi a long time ago. So this is the complex version. It's just a torus. It's just 2 pieces of S1. This is, in fact, a very interesting phenomenon. You think about trigonometry function is a periodic function. Then, so to parameterize the elliptic curve, you need to call elliptic functions. Elliptic function is double periodic. So from this point of view, it's really a new math object in mathematics. So for rational points, you start with elliptic curves. So then, as a Poincare formulate that, the rational points will form a group. That's he observed that. Then he made a conjecture he called the hypothesis. In 1901, in a paper, it's also called arithmetic of algebraic curves. And this is proved by Maudet in 1922. So if C is on the elliptic curve Q, then the rational points and C is finitely generated. Finitely generated means that you have a finitely many points. From these finitely many points, we get all other points by 2 simple rules. From 2 points, you intersect with get 30 points. From 1 point, you take a reflection. The 2 simple rule will get all other points. Sorry, and there's a typo here. So for R, not bigger than 0, for greater equal than 0. R could be 0. So this second one is a finite group. To understand, so the model proof is by contradiction. So in other words, it's not proved by construction. So we have no idea how to find the rational points on the curve. Otherwise, we solve the congruent number problem. He proved that, well, if you have infinitely many, you're going to get contradiction as usual in mathematics. And in fact, in some sense, he used the infinite descent in the proof. So to get the more information, we need to study their arithmetic called modular arithmetic. So if you want to get a die function equation like elliptic curves, right? An equation is difficult to solve, find points over rationals or integers, but it is easier to find the points mod some prime. So once you get a number of these points, then you make this error term. These points most likely is like a p. The reason is you have the probability for each x, you have 50% to get a y, right? So if you get a point of y, you have 2 points. So, so the error is called AP. From this AP, you form a so-called error series or error function. This error function is convergent for real part of s greater than 3/2. This is Hass's theorem. And has a holomorphic continuation of whole complex number. This is exactly the theorem proved by Andrew Wiles in his and completed by other people. So now I formulated the $1 million price problem, the Clay Institute Millennium Problem. So they call it BSC conjecture. I will not write a detail. So the conjecture said that the error series, it was built up on the arithmetic, modular arithmetic, somehow has a very close relation to the rational points on elliptic curve. They said that if you run a tail expansion of this error series at x equals 1, then the order vanish is exactly the rank of the elliptic curve. So in particular, if this error function vanish at 1, if and only if your elliptic curve has infinitely many rational points. So the basic results is not much. So we know. So the Sunday, when I read the citation, I quoted by work of Kurzweil. So first result is by Kurzweil, is that if E has a complex multiplication, and if the error function is non-vanishing, not error cube, sorry, another huge typo, then this rational points is finite. So this implies in particular to non-congruent numbers for n congruent 1, 2, 3, 8. So in other words, for congruent number problem, we have a better results for non-congruent numbers. So then there's another result, the Gross-Zagier-Colli-Wagen. If the error function vanish, but derivative is not vanished, then the elliptic curve has a rank 1 with explicit point called a Hingham point. So this applies. So this actually applies to n congruent to 5, 6, 7 mod 8. Sorry, I prepared the slides yesterday night. So a lot of typos here. So now I give you some geometric way to understand this relation between modular form and the rational points. So here's an idea to construct these points by using modular functions. So this is a punctual of a plane. Then you have a parameterized to this torus. So we know that in a complex world, every torus is parameterized by complex plane. But if your elliptic curve define the rationals, then somehow, miraculously, you use the error function. You can get a parameterization using upper plane. So this is completely arithmetic. It's not a geometric theorem. It's a arithmetic theorem. So now I found a problem in Chinese internet. But in fact, when I go back to check the internet, it's already in the English version long time ago. The internet says that 95% of people cannot solve this problem. Say that you have apple, you have a banana. I don't know what that saying is. Well, then you're trying to find the integers to make this thing to be 4. So then say 95% of people cannot solve this problem. So okay, I'll write it the more simple way. So this is the equation you do. If you algebra geometry, you immediately know this is a elliptic curve because it's simply a cubic equation in P2, right? So this is the minimal solution. Of course, this is just for 4. You can ask for other numbers. It can be very, very complicated. So how people can get this solution? So you can start with a very general equation, A over B plus C plus B over C plus A. This is the equation. Then this is the cubic and projective plane with a rational point. Then there's a standard process in algebra geometry, make this into be elliptic curve. So this elliptic curve, then n equals 4, the E of Q is in fact has a rank 1. It has explicit points. The P equals is 4 minus 1, 11. But unfortunately, the point has one negative number. Then what do? You just simply multiply it by itself until you get all 3 numbers are positive. So when you get a 9, you're very happy. You get 3 positive numbers. That's the solution. Then if you say, I want to start for general n, then it needs BSD. Once you have BSD, then you know how to solve this problem. Okay, so this is the end of my lecture. Thank you.
Okay, thank you very much. I think we have maybe time for 1 or 2 questions. I know everyone is hungry and wants to go for dinner. Are there questions? If not, let's ask our questions over dinner, and let's thank Professor Chu Chang-Wu once.
所有好的东西都要经过实验的考验。
To pose problems and to understand, to have a grand view of what is important, not only to solve problems.
Essentially took almost 20 years to solve them.
你可能没有足够多的工具。
You cannot rush it. Experience shows quickly enough does not help. 它有不可预见性，
像追剧一样，可能这样几年就过去。
还有新的很多的问题涌现出来。
一般好的数学都是花好几年功夫才能够成熟的。当时我们开始中心的时候，小猫2、3次，清华书记跟清华校长这个写生同力的这个。
1、2、3，好，不重要，来这边。
我们要成为一个世界第流的科研教育基地，我们需要产生基础学问，能够对大自然里边出来的问题有深入的了解。你了解一个主要的想法以后它可以分支到很多地方去影响他们。中心成立了15年，我们在科研方面引进了一大批世界一流的学者。
这几年主要关注于微分方程和机器学习的一个交叉。
主要的研究领域是因果推断，包括工具变量。
我的研究领域是拓扑学中的低维拓扑学，
聚焦的是一类从微分几何里来度量的存在性、可计系统以及数论的交叉的联系。
我一开始是做代数表数论，后面我就做一些曲面的一些对称性。
我主要的方向呢是理解这个 ADS-CFT correspondence。
在这种非常 complicated 的 setup 下，你怎么做因果分析？尤其是对于早产儿，有没有一个很大的影响？比如说和医生的交流，比如说和流行病学家的交流，和教育学家的交流。这个是你，比如说1分钟你跳了多少下？基础数学是能够推动应用学科发展非常大的动力。
这2年我们也在探讨用一些机器学习的方法来解一些偏圆方程。传统的偏圆方程的求解方法，我给一个偏圆方程，你去解它1次。如果我这个偏圆方程换了，你要再求解它1次。这一大类解算子，这一大类里面我就不需要再重复的再解它了。你只要告诉我这个偏圆方程，用这个机器学习的方法把你的解给你推断出来。
Basically, what I have finished are those that use the ADS-CFT correspondence field theory to roughly know what the CF.
量子引力理论基本上就是现在高能理论物理的一个空白的一块，到目前为止我们是不知道怎么可以把它们放在一起是一个自洽的形式。如果我们能完整的理解这个对应关系的话呢，我们可能就能给出来一个完整的量子引力理论。
不管怎么评估，都会某地方出现一个尖点，就是说这个4维欧式空间上有无穷多种方式可以做位置。2个带群作用的球面之间什么时候存在一个映射，它的起源叫做11/8猜想，最后给了主塔 Jones 球面映射这个问题的完整的答案。
回到这个identity， 就会大概是一个 a 乘以 b 乘以 a 逆乘以 b 逆这样一个操作。
用一个系统的语言来联系不同方向的一个工具，黎曼曲面这样一个几何背景，然后从三角范畴可以定义一个稳定条件空间。
比如说，你可以画一条线，这个是这个 low 的这个范围，
是议定曲率下的这种度量的存在性。我们特别的考虑双周期的这种问题，它就可以转化为椭圆函数的理论来研究。
这是我们非常得意的一个工作，而且我们的证明方法是原创的。
15年前根本不可能想象请美国名校的老师。
One of the best things about working at Tsinghua is about the students. All this very top talent of China come here.
When I came here, it was very small. The growth is, of course, the most significant change that we have.
本科生他们能够现在就接触到一些超过他们现在普通的课本上面学到的这些知识。
学生能够有勇气，同时敢反问，有好奇心。
接下来最重要的目标就是在中国本土培养出世界第一流的博士研究生。
我们自己的学生越来越接近于国际的前沿水平，大家也对中心这边很有归属感，回来继续建设好我们的中心。
世界一流的学者在清华里边互相交流。
探索这些公开问题，有点像我们爬一座从来没有人爬过的野山一样，就是这些路都不是现成的路。
我们要成为一个世界第一流的科研交流基地，现在还在不停地向前，自己也走一步出来，这样子才能够成功。所有好的东西都要经过实践的考验。
To pose problems and to understand, to have a grand view of what is important, not only to solve problems.
Essentially took almost 20 years to solve them.
你可能没有足够多的工具。
You cannot rush it. Experience shows quickly enough does not help.
它有不可预见性，
像追剧一样，可能这样几年就过去。
还有新的很多的问题涌现出来。
一般好的数学都是花好几年功夫才能够成熟的。当时我们开始中心的时候，小猫2、3次，清华书记跟清华校长这个写生同力的这个。
1、2、3，好，主重号来这边。
我们要成为一个世界第一流的科研交流基地，我们需要产生基础学问，能够对大自然里边出来的问题有深入的了解。你了解一个主要的想法以后它可以分支到很多地方去影响他们。中心成立了15年，我们在科研方面引进了一大批世界一流的学者。
这几年主要关注于微分方程和机器学习的一个交叉。
主要的研究领域是因果推断，包括工具变量。
我的研究领域是拓扑学中的低维拓扑学，
聚焦的是一类从微分几何里来度量的存在性、可计系统以及数论的交叉的联系。
我一开始是做代数表数论，后面我就做一些曲面的一些对称性。
我主要的方向呢是理解这个 ADS-CFT correspondence。
在这种非常 complicated 的 setup 下，你怎么做因果分析？尤其是对于早产儿，有没有一个很大的影响？比如说和医生的交流，比如说和流行病学家的交流，和教育学家的交流。这个是你，比如说1分钟你跳了多少下？基础数学是能够推动应用学科发展非常大的动力。
这2年我们也在探讨用一些机器学习的方法来解一些偏圆方程。传统的偏圆方程的求解方法，我给一个偏圆方程，你去解它一次。如果我这个偏圆方程换了，你要再求解它一次。这一大类解算子，这一大类里面我就不需要再重复的再解它了。你只要告诉我这个偏圆方程，用这个机器学习的方法把你的解给你推断出来。
Basically, what I have been interested in are those that use the ADS-CFT correspondence field theory to roughly know what is here.
量子引力理论基本上就是现在高能理论物理的一个空白的一块，到目前为止我们是不知道怎么可以把它们放在一起是一个自洽的形式。如果我们能完整的理解这个对应关系的话呢，我们可能就能给出来一个完整的量子引力理论。
不管怎么评估，都会某地方出现一个尖点，就是说这个4维欧式空间上有无穷多种方式可以做为两个带群作用的球面之间什么时候存在一个映射，它的起源叫做11%猜想，最后给了Utah Jones球面映射这个问题的完整的答案。回到这个identity， 就会大概是一个 a 乘以 b 乘以 a 逆乘以 b 逆这样一个操作。
用一个系统的语言来联系不同方向的一个工具，黎曼曲面这样一个几何背景，然后从三角范畴可以定义一个稳定条件空间。
比如说，你可以画一条线，这个是这个 low 的这个范围，
是议定曲率下的这种度量的存在性。我们特别的考虑双周期的这种问题，它就可以转化为椭圆函数的理论来研究。
这是我们非常得意的一个工作，而且我们的证明方法是原创的。
15年前根本不可能想象请美国名校的老师。
One of the best things about working at Tsinghua is about the students. All these very top talent of China come here.
When I came here, it was very small. The growth is, of course, the most significant change that we have.
本科生他们能够现在就接触到一些超过他们现在普通的课本上面学到的这些知识。
学生能够有勇气，同时敢发问，有好奇心。
接下来最重要的目标就是在中国本土培养出世界第一流的博士研究生。
我们自己的学生越来越接近于国际的前沿水平，大家也对中心这边很有归属感，回来继续建设好我们中心。
世界一流的学者在清华里边互相交流。
探索这些公开问题，有点像我们爬一座从来没有人爬过的野山一样，就是这些路都不是现成的路。
我们要成为一个世界第一流的科研教育基地，现在还在不停地向前，自己也走一步出来，这样子才能够成功。所有好的东西都要经过实验的考验。
To pose problems and to understand, to have a grand view of this is important, not only to solve problems.
Essentially took almost 20 years to solve them.
你可能没有足够多的工具。
You cannot rush it. Experience shows quickly enough does not help.
它有不可预见性，
像追剧一样，可能这样几年就过去。
还有新的很多的问题涌现出来。
一般好的数学都是花好几年功夫才能够成熟的。当时我们开始中心的时候，小猫2、3次，清华书记跟清华校长这个写生同力的这个。
1、2、3，好，重号来这边。
我们要成为一个世界第一流的科研教育基地，我们需要产生基础学问，能够对大自然里边出来的问题有深入的了解。你了解一个主要的想法以后它可以分支到很多地方去影响他们。中心成立了15年，我们在科研方面引进了一大批世界一流的学者。
这几年主要关注于微分方程和机器学习的一个交叉。
主要的研究领域是因果推断，包括工具变量。
我的研究领域是拓扑学中的低维拓扑学，
聚焦的是一类从微分几何里来度量的存在性、可计系统以及数论的交叉的联系。
我一开始是做代数表数论，后面我就做一些曲面的一些对称性。
我主要的方向呢是理解这个 ADS-CFT correspondence。
在这种非常 complicated 的 setup 下，你怎么做因果分析？尤其是对于早产儿，有没有一个很大的影响？比如说和医生的交流，比如说和流行病学家的交流，和教育学家的交流。这个是你，比如说1分钟你跳了多少下？基础数学是能够推动应用学科发展非常大的动力。
这2年我们也在探讨用一些机器学习的方法来解一些偏圆方程。传统的偏圆方程的求解方法，我给一个偏圆方程，你去解它一次。如果我这个偏圆方程换了，你要再求解它一次。这一大类解算子，这一大类里面我就不需要再重复的再解它了。你只要告诉我这个偏圆方程，用这个机器学习的方法把你的解给你推断出来。
Basically, what I have finished are those that use the ESFP correspondence field theory to roughly know what the
量子引力理论基本上就是现在高能理论物理的一个空白的一块，到目前为止我们是不知道怎么可以把它们放在一起是一个自洽的形式。如果我们能完整的理解这个对应关系的话呢，我们可能就能给出来一个完整的量子引力理论。
不管怎么评估，都会某一方出现一个尖点，就是说这个四维欧式空间上有无穷多种方式可以做位置。两个带群作用的球面之间什么时候存在一个映射？它的起源叫做11%猜想，最后给了主塔 Jones 球面映射这个问题的完整的答案。
回到这个identity， 就会大概是一个 a 乘以 b 乘以 a 逆乘以 b 逆这样一个操作。
用一个系统的语言来联系不同方向的一个工具，黎曼曲面这样一个几何背景，然后从三角范畴可以定义一个稳定条件空间。
比如说，你可以画一条线，这个是这个 low 的这个范围，
是议定曲率下的这种度量的存在性。我们特别的考虑双周期的这种问题，它就可以转化为椭圆函数的理论来研究。
这是我们非常得意的一个工作，而且我们的证明方法是原创的。
15年前根本不可能想象请美国名校的老师。
One of the best things about working at Tsinghua is about the students. All this very top talent of China come here.
When I came here, it was very small. The growth is, of course, the most significant change that we have.
本科生他们能够现在就接触到一些超过他们现在普通的课本上面学到的这些知识。
学生能够有勇气，同时敢反问，有好奇心。
接下来最重要的目标就是在中国本土培养出世界第一流的博士研究生。
我们自己的学生越来越接近于国际的前沿水平，大家也对中心这边很有归属感，回来继续建设好我们的中心。
世界一流的学者在清华里边互相交流。
探索这些公开问题，有点像我们爬一座从来没有人爬过的野山一样，就是这些路都不是现成的路。
我们要成为一个世界第一流的科研教育基地，现在还在不停地向前，自己也走一步出来，这样子才能够成功。所有好的东西都要经过实验的考验。
To pose problems and to understand, to have a
对我来讲，数学是科学界或者学术界人们唯一的真理，没有个东西能够比数学纯真，同时真正表现出来这个真理，不会随时间来改变的。同时，现在我想是可以讲是一个黄金时代，对中国来讲，我希望能够帮忙中国达成这个，趁这个机会能够达成中国在基础科学上成为世界第一流的这个唯一，可能讲是唯一最重要的机会。中央支持这个学生有很好的学生，所以这整个环境是很好的环境。
We are also able to recruit a very distinguished cast of senior mathematicians from abroad.
I'm Coach Birka. I'm a mathematician, a professor of mathematics at the Yale Center for Mathematical Sciences in Tsinghua University. We have a very vibrant research environment here, and I hope that you also come and join us. And welcome to Beijing.
I feel that, there are plenty of young people who dream of this place. And I felt that I need more time for research, more time for sort of more creative things. And then Yao approached me, and I thought that this is a wonderful opportunity. So that's my decision.
I'm happy to witness the rapid development of recruiting talents on board. The majority of them, two-thirds of them are young assistant professors. They got their degrees from prestigious institutions such as Harvard, MIT, Princeton, Columbia, Yale, UC Berkeley, etc.
有很多人说数学是一个基础，但是如果从研究发展来说，数学是最顶层的。如果你数学搞不好，你很多的科技都搞不好。所以我们是希望可以在这个最顶层的数学这一方面有自己的想法，有自己的人才。
I'm happy that we have nice working conditions, and I really hope that I could contribute to make the mathematics develop better.
我觉得现在清华这边国际的数学大师以及年轻有为的数学家都变多了很多，然后我们的课程和这个讨论班都丰富了很多，完整了很多。
I have been impressed that it's certainly still at the beginning, but promises to be a major development, not just for China, but generally this is going to be a big center for the world mathematics.
推动数学的发展不但是中国，也全世界的。我对于培养年轻人一向都有很大的兴趣。我们要集中精神，将这个明年100个学生能够教成最前沿的，能够懂得最前沿的数学，让他们追上这个世界水平。同时毕业以后能够带领全国的数学的进展，数学的学科的最前沿的研究，这是我们的宗旨。所以我们要培养精英里边的精英，基础里的基础。看的都是世界，从整个世界的观点，整个世界学术界的观点来看，一定要跟全世界最好的这个大学、最好的研究机构相比，也要解决很多世界最前沿的数学问题，让这个世界的数学能够上一个台阶。
加快建设教育强国、科技强国、人才强国的号令已经吹响。作为支持清华大学发展数学学科的重大战略举措，2014年底，教育部同意依托清华大学成立丘成桐数学科学中心。中心成立之初就以高水平人才引进、造就新一代世界领先数学家为根本任务，以培养世界一流数学家为目标，建立了全方位、立体化的人才培养机制。 激发中学生兴趣和创新能力的丘成桐中学科学奖，全面测试本科生专业知识、修养与能力的丘成桐大学生数学竞赛，鼓励更多女生投入数学学习的丘成桐女子中学生数学竞赛，旨在鼓励全世界杰出的华人数学学子追求数学真理，激发研究者创新研究热情的最佳论文奖，世界华人数学家大会面向年轻数学家设置的多个奖项，目前已经形成中学阶段兴趣培养、大学阶段基本功夯实、研究生阶段鼓励科研创新的独特人才培养体系，不断促进着中国从中学到大学数学教育的全面改革。近年来，在丘成桐先生的带领下，数学中心2021年引进了菲尔兹奖得主丘成桐教授，以及国际一流数学物理学家 Nikola Rashtikin。今天，数学科学面临前所未有的历史机遇，数学中心将秉持开拓、创新、谋长远的发展宗旨，面向国家战略需求，瞄准世界科技前沿，凝聚师生力量，齐心协力，扎实工作，在培养高素质一流创新人才，取得国际原创性科研成果，创建世界领先水平的数学学科及师资队伍方面取得突破性进展，为建设成为世界一流数学基地，为清华大学建设世界一流大学和中华民族伟大复兴而努力奋斗。加快建设教育强国、科技强国、人才强国的号令已经吹响。作为支持清华大学发展数学学科的重大战略举措，2014年底，教育部同意依托清华大学成立丘成桐数学科学中心。中心成立之初就以高水平人才引进、造就新一代世界领先数学家为根本任务，以培养世界一流数学家为目标，建立了全方位、立体化的人才培养机制，激发中学生兴趣和创新能力的丘成桐中学科学奖，全面测试本科生专业知识、修养与能力的丘成桐大学生数学竞赛，鼓励更多女生投入数学学习的丘成桐女子中学生数学竞赛，旨在鼓励全世界杰出的华人数学学子追求数学真理，激发研究者创新研究热情的最佳论文奖，世界华人数学家大会面向年轻数学家设置的多个奖项，目前已经形成中学阶段兴趣培养、大学阶段基本功夯实、研究生阶段鼓励科研创新的独特人才培养体系，不断促进着中国从中学到大学数学教育的全面改革。近年来，在丘成桐先生的带领下，数学中心2021年引进了菲尔兹奖得主丘成桐教授，以及国际一流数学物理学家 Nikola Rashtikin。今天，数学科学面临前所未有的历史机遇，数学中心将秉持开拓、创新、谋长远的发展宗旨，面向国家战略需求，瞄准世界科技前沿，凝聚师生力量，齐心协力，扎实工作，在培养高素质一流创新人才，取得国际原创性科研成果，创建世界领先水平的数学学科及师资队伍方面取得突破性进展，为建设成为世界一流数学基地，为清华大学建设世界一流大学和中华民族伟大复兴而努力奋斗。加快建设教育强国、科技强国、人才强国的号令已经吹响。作为支持清华大学发展数学学科的重大战略举措，2014年底，教育部同意依托清华大学成立丘成桐数学科学中心。中心成立之初就以高水平人才引进、造就新一代世界领先数学家为根本任务，以培养高素质一流创新人才，取得国际原创性科研成果，创建世界领先水平的数学学科及师资队伍方面取得突破性进展，为建设成为世界一流数学基地， 为清华大学建设世界一流大学和中华民族伟大复兴而努力奋斗。加快建设教育强国，
对于我来讲，数学是科学界或者学术界人们唯一的真理，没有个东西能够比数学纯真，同时真正表现出来是个真理，不会随时间来改变的。同时，现在我想是可以讲是一个黄金时代，对中国来讲，我期望能够帮忙中国达成这个，趁这个机会能够达成中国在基础科学上成为世界
next, we come to the highlight of our evening, the panel discussions with some of the brightest minds, most brilliant and successful minds in the world. I will introduce the panelists, and perhaps I think as I introduce, you could come to the stage. We have this seating assignment over here. So our first honored guest, Fields medalist and member of the U.S. National Academy of Sciences, Professor Artur Avila from University of Zurich. Please welcome. From University of Zurich and IMPA. Next, Fields medalist Professor Kaushal Pirkar from Tsinghua University. Next, we have Fields medalist and member of both U.S. National Academies, Professor Andrei Okunkov from Columbia University. Next, Wolf Prize laureate, Professor Andrew Wiles from Oxford University. And last but not least, Tsinghua University Chair Professor, Director of Yale Mathematical Science Center's Fields medalist, foreign member of the Chinese Academy of Sciences, member of both U.S. National Academy, Professor Xingtong Yao. Okay, it's a great honor to be here on stage with all of you. We have some questions prepared. We were hoping for a somewhat spontaneous evening. We have some. So I wanted to start with the first question. Preparation. We have this. We've just seen 85. Actually, there was 88 Mathematical Frontier of Science awards given, and last year there were 85 awards given in mathematics, and this is a once in a lifetime thing that's it's kind of never happened before. And I would like the first question, and I'll give I think everyone a chance to tell us about what you think about this event. Like, what are your thoughts? And I think perhaps we should start with Professor Yao, who is the president of the ICBS. Why are we doing the ICBS? What's your vision? What do you hope for it?
Well, I've said it several times, and I mean it. We set up the ICBS during the COVID time, actually. COVID just over. We have been hungry to build a good relationship with the whole world. We have not been able to travel, and we open up. Many of our friends all over the world are interesting to come to talk with us. And we have to find some means to attract them and also to communicate well. So we set up this ICBS as a congress for 3 different subjects, physics, math, and information and computer science. I always felt that these are 3 important subjects that should be really cooperate on understand intelligence in science and in many different fields that could be important for mathematics and for physics and for the computer science themselves. I think human beings will benefit a great deal by interacting instead of isolate themselves from each other. And in fact, I like to read Chinese history. Each dynasty flourished But starting around Ming Dynasty, Chinese, although was rather strong, they close up themselves. They don't communicate with Europeans. And then we see the intellectual creativity start to decay all the way to Qing Dynasty. When the Roman Renaissance starts, and then you see the flourish of the science and technology in Western world. Chinese were not able to capture any of them. Until 19th century, we start to know calculus. That was way too late, and it takes a long time for us to recapture what was missing. We are still behind, but at least now we open up. And I think it was a great policy by Deng Xiaoping about 50 years ago now, 45 years ago, to decide, Chinese government decide that society has to open up at all costs. Despite in the last 40 years, we see up and down, difficulty and all that, but the leaders of China insist the open policy for the Chinese people is utmost important. So all the way up to now is an open policy. And I think this is very important. And I thought about this is partially to uphold this open policy. It's not just for science, but also for people to come in to understand China, to communicate with our students and our scholars. I think we will be able to promote culture, promote science, promote mathematics in a very fast manner. It will be beneficial to humankind in general. And I mean it in that way, and I feel very happy to see the flourishment in the last 2 years. And now what I think is something that I want to do in the sense that I saw, especially in China, the promotion of many people are based on some unjustified propaganda without knowing the real understanding of mathematics behind it. Now, our award was based on many people's expressed opinion. And sure, we actually use a lot of their time, but I think at the end, it has been completely justified. You see, we have 88 awards in, in different subjects, and I think they were well chosen. If they were not chosen this year, they will be chosen by different group next year. So it covers from 5 years to 10 years period. I think any good paper would be chosen in due time. And while there's always some small error, but the error is small enough, I think we can discount it. So I think any people who got award, they got it because of their own strength and because of the paper's strength. And I think this should be important. For a young mathematician, when they know their paper was recognized because of its strength, I think this will encourage them to go very far. And not based on politics, not based on you know who and all that. So that's one of the reasons I feel about it. As for the Lifetime Award, I think it stands out by itself. For example, this time we have, of course, Andrew Wise, we have Hamilton, we have Witten. All these are great mathematicians. Every people look at it as a big star now. In fact, our students, children college students, said that now we see the real star. They read all these people's names in the book, in textbook. Now they actually see them. I think this is a very exciting period for young guys. They see the people to actually create a field. I think it will make a lot of difference for them. So I think both the Lifetime Award and the Paper Award are good. Maybe we should create more, but at this moment, I think this is a good thing. Thank you.
Thank you very much for sharing your vision with us. So indeed, one thing that Professor Yao has mentioned many times is that he really wants our students in particular to see these giants. These are human beings that are maybe just like every one of us, and bringing them up close and personal for our students to interact with. And you mentioned interaction between many different cultures. I'm thinking about yesterday, Andrew Yao, Lifetime Award winner, Andrew Yao Ji Chi. He mentioned how in computer science, now it's not just about computation cost, but it's also the communication cost that's one has to take into account. And I would imagine that the ICBS is moving in the direction of now maybe I don't know if I have volunteers, or maybe I should Professor Lifetime Award, Professor Andrew Wiles, would you like to say a few words what you think about the ICBS and its role it could play?
Yes, well, I completely agree with Professor Yao. I think mathematics has always thrived on unity of time and space. So one cannot imagine doing mathematics if we had to restart each generation from scratch. We depend on all our ancestors. It's the same in place. We depend on people in other countries, on the mathematics that's done everywhere in the world. Personally, I would not be the mathematician I am if I'd not been able to go to the United States, because at that time, all the best people in my field were there. It was a very exciting experience, and I learned a great deal from that, and I took it back home with me when I came back to England. And I hope the same will work both ways with China. Chinese will learn from the rest of the world. The rest of the world will learn more from China. I think it's a wonderful congress and a wonderful innovation.
Thank you, Professor Wiles. And in your beautiful presentation yesterday for the Lifetime Award, I was really impressed how you mentioned not just the accomplishments in number theory, but also mentioned dynamical systems, and like there's the mathematics that you do involve many different fields. Now, maybe what I want to do is I try to think of some questions that maybe the audience members here want to ask. And so I want to bring kind of a change the subject a little bit. I want to share with you a colloquial term that I learned in China. I heard the president of the Tsinghua University use this before, so I think it's okay. It's called YYDS. I will explain what this acronym means. It means you are forever godlike, okay? And so, and each and every one of you here have essentially achieved that status, and a lot of us would love to know like how it feels. So, but I'm not gonna ask you about that. What I would like to ask is, it sounds like, okay, if you're Professor Yao, you're a teenager or maybe young 20s, and you see Calabi conjecture and you go solve it. Okay, maybe you didn't solve it the first time, but in 3 years, then you did it. Professor Wiles, Fermat's last theorem from his childhood, and spent 7 years in the Princeton attic. That's the story we hear in the news. And you solve it. It's like a fairy tale come true. But my question is, have you ever been scooped? I think we could have similar stories for everyone. But I want to learn about your stories about like a problem that maybe you spent a lot of time working on and someone else got to it first. Are there stories like this that you can tell us? Anybody want to go first? Professor Bjorkar, please, thank you.
Well, it happened to me, but in a good way, not in a negative way. I think there were maybe 5 or 6 times that I did something and then I realized that someone else were doing something very similar, very close, but all turned out very well. I mean, so none of us really were affected negatively. You know, at least in my field, if 2 people publish something in the course of a couple of weeks, everyone assumes they were done independently. It's not like some other field outside mathematics. So I think at least 5 or 6 of my papers were, when I put them on archive, someone else did just a couple of days, a few days or a couple of weeks after, or they did 1 or 2 days before me. But I think no one were really negatively affected. Everything was published and fine.
Okay, thank you for sharing. I was wondering if okay, we could also change topics if you don't unless okay, I have more questions. So okay, what about so my question is then, like, how often does it happen? Like once a year, several times a year, or like this kind of thing being having, well, it's not really being scooped, I guess. That's your story is really happening at the same time. Okay, I maybe asked that question because I've been scooped many times. Okay,
maybe I can answer you.
Okay,
I think nobody's school, because we work ideas, and some arrived at earlier, some arrived a little bit later. But whenever you spend effort on it, you always got results, one way or the other. You may not solve this problem before the other guys this time, but the similar idea you learn, and you learn it in a fruitful manner, you will solve other problems. And they are always very fruitful, I think. So let me give you an example. When I was in Stanford, Rick Strand and I was working on harmonic maps. We did the case where Riemann surface is homogeneous, and we are thinking about to do the sphere case. I don't know whether Rick still remember yet. Then I opened the notices, I found Ken Wunberg has done it, Sachs Wunberg. And look at the paper, I really admire what Sachs Wunberg has done, beautiful work, and I learned the idea. And then I really learned it deeply because I was trying to do it, I couldn't do it on time. Then I make use of it to solve several other problems. My work with Seal on the Frankel conjecture was based on that, but I understand it deeply. And I solve other problems also using similar ideas. So I think you don't have to feel bad when you do something, some other people arrive there first, but because you master the technology, you will be able to do some other things. And just by keep on thinking about it. I know this, I think, is a very healthy thing to happen, as long as you don't steal from other people completely, or the other people steal from you completely. But competition is good.
Okay, thank you for the nice answer. Okay, I have, when students come to me, I give them advice, which is you should not be afraid to make mistakes, because you will learn more from them than from your successes. And I don't know if that's good advice. Can I maybe get some opinion from some of you here about, do you feel that you've learned more from your mistakes or more from your successes?
You know, there's a prior for everything, right? There are many more mistakes than successes. Therefore, you learn much more from them.
Okay, so I think my advice is correct.
maybe I say a kind of counter
Okay.
answer.
All right.
Yeah, I think I learn mostly not from success nor from mistakes. I just learn from thinking about some problems, about thinking about other people's questions, and also thinking about asking my own questions. That's where I learn the most, either by creating something new or that I'm forced to look at other people's work. That's when I learn the most, I think.
Okay.
Yeah, I remember one time I was working with Barry Mazer and we got something wrong, and he was very excited because he said, that just makes it more interesting. And it did, but it took a little while to convince me. Yeah.
It's a compliment when someone like Barry Mazer says that.
Yeah. But I agree that you learn from mistakes. I think in some sense, mathematics is trial and error. And you just have to publish it when you're not in the error period. You have to gone past the error and then publish. It's better.
Okay. All right. Okay. You all seem very confident, and I think a lot of us also want to feel like know how you do it. And I think one question that we maybe all have is like you learn a lot of math, but how do you stay sharp? Maybe I could help more precisely what I'm looking for. Like I think hard work is very important, and like certainly we all know you're very talented, but we also believe, I believe that hard work is an important part of it. And to work really, really hard, you have to be very driven. And I would like you maybe to reflect upon your own career. Like in the beginning, how hard did you work? I'm sure probably you work very much harder than most other people. But what about after like your successes? Did you work even harder, or did it become easier? How does it feel? How hard do you work? Can you let us on that? I know Professor extremely hard.
My friends are all hard workers. My neighbor in Stanford was Leon Simon, who worked very hard. But he has a family, so it turns out I work harder than him. So in the young days, I worked almost 15 to 16 hours per day. But I felt fun, and I enjoy it.
But you didn't answer my question. Did you work harder like after you got all these prizes or before? Like, well, maybe I put it this way. Like when I started out, I was thinking, okay, I'm gonna find some nice conjecture that I want to work on. Then I'm gonna spend all my energy working on it so that when I solve it, then I can do whatever I want after that. Is that the right philosophy?
Not really. Well, in 1976, I solved the Calabi conjecture, and somehow I got instantly famous by the end of 1976. But I do not feel that I should not work, and I actually immediately changed to work on some other subjects, minimal surface. I worked with Bill Mix on solving the embedding problem and some topological questions. I just found that exciting when I see an interesting problem. And I don't feel I will stop because it's so exciting to look at those beautiful problems. That's all it counts to me.
It sounds like you worked even harder afterwards.
I won't say even harder. I just enjoy it. I feel good to work on it.
Okay.
Yeah.
Atul, you want to?
Then I solved the positive mass conjecture with Rick by 1977, 1978. So there was a very fruitful years, I would say.
Yeah, so I think that's helpful as just a general comment that there is some advantage as time goes by that which is not clear at all. Things that are not clear at all when you start become more evident. Like when you start, you're very worried about if you can succeed at all on problems. And there is also some kind of constraints. You're in the beginning of your career, and maybe a lot of things will be defined by some chance events that maybe you are starting to work, and one problem may determine what happens in the immediate future, if you get a position, or maybe you have some problems in your beginnings, and you get very obsessed about getting your paper published in the best journal possible, and then sometimes it's something unfair happens, or maybe you get unlucky and someone scooped you and you get worried. So many things affect, but with time, there are many more events, and some just randomly, some will be beneficial and something will not be. You just get used to it, and you don't get so fixated on any specific thing. And with this attitude, you are kind of much more relaxed with respect to this. You keep working as much, but whenever something bad happens, you think that at some point something good will happen. You just wait, and you know that the scale where things happen is years, so you don't kind of expect for next month a compensation, but you just wait for time to put things fine for you again. I think it's a relaxing attitude to avoid, otherwise you get too obsessed and it's bad for you.
Thank you.
Can I ask on the previous question in terms of learning? And actually, I learned the most from other people, and in fact, the event like this, it's a great chance to talk to people and get explain something in simple words, just the essence of things. It's you get to the essence of things much quicker than by trying to read the papers from the beginning. Like for instance, my very good friend David, who's napping there in the first row, he got me into automorphic forms somehow, and I learned. Of course, he understands things so deeply. I just ask him, and he I see him. I haven't seen him since 2018, and bringing people together in one place where just can explain to each other in simple human way that what's the most important thing, where do you have to look at. That's just priceless. And I certainly, BIMSE is rather unique in this way that it or maybe China in general, but specifically BIMSE is an amazing place where you can bring people from every single country in the world, and they can talk to each other. There's so many people around in this meeting I want to talk to, and I want to learn something from them, maybe explain something in return. And the second thing is in terms of maybe second what Artur was saying. For me, it's also very important to let the things you already put in your head, let them roll there a little bit, and until until kind of the key sinks into the hole. You need some time for things to settle, and that's also extremely important. You shouldn't forget that. And so it's great that here at BIMSE there's above us a very nice park. If you need to go for a meditative walk, you can just go up there, and especially in the morning or the evening. And that's for me this kind of thing, when you go and walk and think about something, that's extremely important.
Thank you for those insights. Professor Wiles, yes?
Yeah, for your question about working hard, it's like asking a gambler how he keeps going. I mean, where mathematics, we enjoy it so much. The problem is not to work hard, it's to stop working when we need to. And yes. I say, for the sake of your own sanity, for the sake of your family and so on, at some point you have to do other things in life too. And I have to say, having a family, and especially having young children, they are not going to listen to excuses why you need to work. So I think that's, to spend time with your family takes you from your work. There's nothing else I really want to do besides that. So it's not a problem of working hard, it's a problem of stopping when I have to.
It's an addiction. Love for math. Okay. Well, do we have, I think we still have time, and we could open it up to people in the audience. If you have questions, I think we have some staff. Is there a question over there? Now, I think we should have some ground rules that questions should be questions, should not be speeches. And okay, was there a question over there? Oh.
I would like to ask, currently, what is the most exciting field in mathematics, excluding your own one?
Wow, that's a challenging one. Okay, the question is, for anyone to answer, what is the most exciting field in mathematics besides your own?
Okay, maybe I think that's the answer was there already, but you kind of removed it.
Oh.
I think the most exciting field is what excites you the most. That's what you should. That is, I mean, for you, of
course.
Partially answered. Also related to the previous question about work hard. In addition, what is a very strong internal drives you, whatever, that's mathematics or anything. And if you are very excited by any field, any problem in mathematics, then that's what you should go for, because that's probably also gives you the most chance of being successful. Because if you are not excited by whatever, then I think, well, you can succeed up to a certain extent, but to a very high level, working hard is simply not enough. It's necessary, but not enough. But you need really a very strong internal drive. I had a friend when I was a PhD student, I think he put it maybe in the most beautiful way. He said, you should be so motivated that if you don't think about it one day, you get stomachache. I think that's how it should be.
I would like to follow up on your answer. The drive is very important, you say, and but now we're very curious, and maybe any of you can answer this, is where does your drive come from?
It's internal, it's not external. I think it has to be.
Okay.
To reach a really top level in any field, even business. You know, people, if they are purely motivated by collecting money, then they will not succeed. Because I think the most successful people in business, they probably don't care about money. It's just the fact that they are so motivated to succeed or whatever. This drive is internal. That means you are very highly excited by some quest, whether it's a mathematical question or physics or arts or politics or anything. That strong drive can only be internal. It cannot be external. And then the question is how to find it.
Yes.
But I think that is a challenge for young people throughout their school years and also maybe undergraduate to find what they are really most excited about, most they have to, I think, concentrate on those areas that excite them the most. They will have the best chance of success, I think.
I think a lot of our young students and maybe even young faculty, well, they're certainly working very hard, and but they probably always have this question, like, is it internal? It's hard to determine, and yeah, if yeah, why do so hard?
Well, I mean, mathematics is beautiful, and when we look into one problem, we know that if we can solve it, it will give a much deeper understanding of the whole subject. That always excites me, because by solving one problem, you can understand maybe 100 other problems. I think this is the most exciting period for me. There are several problems I solve, I feel in that way. I work with Ken Wunberg on the excisional Hermitian-Young-Mills connection. When I work on it, I felt this is a very general construction. Once I solve it, I bring in a new tool in the subject of vector bundles, which is not so well understood yet at that point. So this excites me, and I feel very good to work on the problem. And actually, I spend more time on that than other problems, actually.
Thank you. Yes, so it has to be, if there's any right and justice in the world, you see problems that you want to know that they're true, because if it's true, it simplifies, explains a lot.
Think those right language when you're talking, I mean right mathematical language. And what do you think, what are the right notions of the future mathematics on which should one work nowadays?
The question is, what are the right notions for the future of mathematics?
Yeah, of the future mathematics, of the mathematics of the future. I mean, like categories comes instead of sets, and nowadays categories is areas of mathematics. And what will be next?
Andre, I guess that's yours.
I can just respond by maybe telling two stories about it. One is a famous quote from Willard Gibbs, a great American physicist. They once had, he spoke once in Yale faculty meeting. On the following occasion, there was a long discussion whether one should learn more languages or more mathematics. And Gibbs listened to that for a while, then got up and said, mathematics is a language. Then, and the second story, one funding agency is decided that that they will look for the most important concepts in mathematics and find research there in that area, and they decided a very, very important notion in mathematics is the identity. And so so I think it's maybe one over lunch yesterday I heard a very wonderful phrase. I'll just repeat today. Is somebody said there are many theories and people to know concrete math, some actual problems that you can get your teeth on and somehow get some feeling of what's going on, and that in this way progress forward.
Okay, I hope that was a good enough answer. I think we have time for maybe one.
Let me answer.
Oh, you want to? Okay, please.
Mathematics language is to use to describe nature. Only those languages that could adequately to describe nature will survive. You can be extremely fancy, but if nature does not choose your language, it will disappear. So you can be extremely fancy, but you don't have enough content, it will disappear by itself. That's my belief.
Okay, I see a hand in the middle, right near the white shirt. Maybe I can. Oh, there, it's coming.
This question I'd like to ask Okokov. And some people believe that Russia is a nation good at algebra and representation theory. And what do you think about this opinion?
He chose you.
It's partially correct, but only to a small fraction. Like for instance, my own. I mean, when I was finishing university, everybody in Russia gets assigned every single profession in the country gets assigned some number, and my particular profession was number 010101, which means in the most important category, in the most important subcategory, it's the most important profession in all of the country, and that was mathematical analysis. So.
Okay, so for your answers and